In recent years, major developments in renewable energy have been driven by the growing global demand for energy and increasing environmental concerns. Traditional energy sources such as petroleum and coal are limited and harmful to the environment due to pollution and greenhouse gas emissions. One of the most promising renewable energy technologies is the solar photovoltaic, or PV, cell. Solar PV cells work by using the photovoltaic effect, which converts solar radiation directly into electrical energy. Solar photovoltaic, PV, is one of the most effective methods to harvest solar energy. The device consists of two semiconductor layers, the P-type and N-type layers. These layers work together to form an electric field. The solar PV system operates by converting solar energy into electrical power through the photovoltaic effect, where sunlight excites electrons in the semiconductor layers, generating electricity. In general, solar PV technology is classified into 4 generations. Our research specifically focuses on cadmium telluride thin-film solar cells, which fall under the 2nd generation of thin-film solar cells. These cells use cadmium telluride, as the primary material, offering a cost-effective and efficient solution for solar energy production. Cadmium telluride thin-film solar cells face challenges like recombination, which leads to the formation of a Schottky barrier at the metal-cadmium telluride back contact interface. Cadmium telluride has a high work function of 5.7 electron volt, which is higher than other metals, forming this barrier. This reduces hole collection and affects VOC, fill factor, and overall performance. To reduce the barrier width, a metal work function greater than 5.7 electron volt is needed, but no commercially available metal meets this requirement. Our study employs density functional theory, DFT, simulations to investigate how dopants like copper, Cu, aluminium, Al, and gold, O, affect cadmium telluride performance. For accurate modeling, we used a 4x4x4K point grid and set energy cutoffs at 52 Ri for work function calculations and 600 Ri for charge calculations. The generalized gradient approximation, GGA, method was applied, ensuring reliable results for both cadmium telluride and its doped variants. We selected Cu, Al, and O as dopants for cadmium telluride due to their potential to modify its electronic properties. The goal was to optimize the bandgap, aligning it with theoretical predictions for efficient solar energy absorption. By doping cadmium telluride, we expect to enhance the bandgap, improving its ability to capture a broader portion of the solar spectrum and convert it into electricity. The dopants were chosen based on their influence on conductivity and bandgap, as well as their interaction with the cadmium telluride lattice, which is crucial for solar cell performance. After selecting Al for doping in cadmium telluride, the simulation used a supercell with 32 atoms, 16 CdTe and 16 Te, arranged in a cubic lattice. The study analyzed bulk cadmium telluride, baseline, and Al-doped cadmium telluride at doping concentrations of 3%, 6%, 9%, 12%, and 15%. Al-doping alters the atomic bonding and local structure, impacting the material's electrical properties. We used SCAPS1D to simulate the IV and QE characteristics of CdTe and Al-doped cadmium telluride for solar cells. Doping levels of 3%, 6%, 9%, 12%, and 15% Al were tested. IV simulations measured VOC and JSC, while QE simulations assessed light absorption and conversion efficiency. Parameters like bandgap were obtained from DFT outputs. Let's explore the bandgap of CdTe and its doped variants. Pure cadmium telluride, 0.73 electron volts, baseline. Cadmium telluride, Cu, 13%, bandgap of 0.49 electron volts, P-type doping, increases conductivity. Cadmium telluride, Al, 13%, bandgap of 0.61 electron volts, N-type doping, improves carrier mobility. Cadmium telluride, O, 13%, bandgap of 0.18 electron volts, deep-level acceptor doping, may reduce performance. In conclusion, doping cadmium telluride with Cu, Al, and O significantly affects its bandgap and conductivity. Copper enhances conductivity. Aluminium offers moderate tuning of the bandgap. Gold causes a substantial reduction in the bandgap. These modifications make cadmium telluride more versatile for a range of photovoltaic applications. Cadmium telluride has a 0.73 electron volts bandgap, Ideal for photovoltaic and optoelectric applications, with the Fermi level at 5.5623 electron volts. Doping effects. Cu doping introduces localized states near the valence band, improving p-type conductivity. Al doping affects delocalized states near the conduction band, enhancing n-type performance. O doping causes hybridization near both bands, reducing the band gap, which may limit standard photovoltaic efficiency. In conclusion, the density of states, dose, analysis shows how dopants like Cu, Al, and O affect the electronic properties of cadmium telluride. Each dopant introduces unique characteristics that enhance the material's performance, making it suitable for applications in solar cells, spintronics, and optical devices. This graph shows the PDOS and TDOS for undoped cadmium telluride, with a key feature at 0.61 electron volts above the Fermi level, essential for conductivity and optoelectronics. Spin asymmetries. CdTe and CdD orbitals suggest potential for spintronics. CdPDOS, dominated by CdS, p, d orbitals. TePDOS, affects valence and conduction bands. Applications. Cadmium telluride is ideal for spintronics and solar cells. The graph also shows how Al doping shifts the Fermi level, impacts spin polarization, and enhances spin-polarized charge transfer, making it useful for spintronic devices like spin transistors and magnetic memory. In conclusion, the PDOS and TDOS analysis highlights CdTe's potential for spintronics and solar cells, with spin-polarized states and a tunable Fermi level. Al doping enhances spin polarization, making cadmium telluride suitable for spintronic devices and next-generation technologies. The dose differences for cadmium telluride and Al-doped cadmium telluride at various doping concentrations are shown. Using a 2.38 ratio from calculations, we match the DFT values to theoretical data. As Al doping increases from 3.13% to 12.50%, the dose gap rises, with the material being optimal at 9.38% Al doping, achieving a band gap of 1.93 electron volts. At 15.63% Al doping, the dose gap closes, indicating potential structural defects and decreased performance. Band gap values: 1.45 electron volts, bulk cadmium telluride, 1.64 electron volts, 3.13% Al, 1.71 electron volts, 6.25% Al, 1.93 electron volts, 9.38% Al, 1.99 electron volts, 12.50% Al. Beyond 12.50%, the band gap drops to 1.05 electron volts, suggesting structural defects and reduced electrical properties. Our results show that 6% to 10% Al doping provides the best balance between enhanced electronic properties and material stability, making it ideal for optoelectric and photovoltaic applications. This result compares baseline cadmium telluride and 12% Al-doped cadmium telluride, showing the impact of Al doping on the band diagram. Baseline cadmium telluride, 1.45 electron volts, has a large Schottky barrier, which hinders hole injection at the back contact, negatively affecting device performance. 12% Al-doped cadmium telluride, 1.99 electron volts, reduces the Schottky barrier, improving hole collection and electron conductivity, making it more suitable for solar cells. This result shows how Al doping affects cadmium telluride solar cells. VOC and JSC improve with 6% to 9% Al doping, peaking at 9% Al doping, enhancing solar cell efficiency. Quantum efficiency, QE, increases with up to 9% Al doping, improving light absorption and overall performance. However, at 12% to 15% doping, both QE and JSC decrease, indicating structural defects and reduced light absorption efficiency. In conclusion, Al doping improves cadmium telluride solar cell performance up to 9%, enhancing VOC, JSC, and quantum efficiency, QE. However, doping above 12% introduces structural defects, reducing performance. 6% to 9% Al doping offers the best balance of efficiency and stability. With our research on Al-doped cadmium telluride solar cells, the ideal target market includes solar energy companies, electronic manufacturers, and industries focusing on sustainable energy solutions. The improved efficiency and stability at 6% to 9% Al doping make it a great fit for solar panels, optoelectric devices, and spintronics, offering enhanced performance and cost-effectiveness for commercial and industrial use.